Let's get started on our week 3 chapter here. All right, and this week we'll be introducing our first functional group. We'll sort of talk about properties of our functional group. We'll talk about how to name our functional group, and then finally talk about reactions. And that's going to be a really typical layout of how this course works. Generally speaking, in each week we'll introduce a new functional group, a new category of molecules, and we'll always sort of be discussing the same basic things: physical properties, nomenclature, and reactions. All right? Cool. So our first discussion is of alkanes. Remember, these are compounds that contain only carbon and hydrogen. And what type of bonds? Only single bonds. Okay? They're a very natural starting point because they're kind of the simplest functional group that you can have in organic chemistry. All right, so we're going to first talk about what we call physical properties of our functional group alkanes. All right, so importantly, carbon and hydrogen on our periodic table have very similar what's called electronegativity. All right, so those two atoms, when they're in a covalent bond, none of them is really winning that tug of war over that pair of electrons. There's a very even distribution of electrons in these molecules, which means that they're just about as nonpolar as you can get as far as functional groups go. So alkanes, very nonpolar. Okay? There's really nothing less polar than an alkane in the world of organic chemistry. All right? So one direct consequence of being nonpolar means that your interactions with neighboring molecules are very weak. So we have very weak what are called intermolecular interactions. Okay.
That, it takes less energy to split them apart?
To break them apart from neighboring one another. So if you had two of them interacting, they're interacting very weakly with one another. So you don't have to put a lot of energy in to separate them. So by intermolecular, I mean the interactions between neighboring molecules. So I'm not talking about the covalent bonds that are holding those carbons and hydrogens together. I'm talking about the interactions between neighboring molecules, right? If you have a beaker of an alkane, you have, 10 to the 24 or something different molecules floating around, a huge number of molecules floating around. I'm talking about the interactions between neighbors, okay? So one way that we measure these intermolecular interactions, or a good stand-in, so we can measure these intermolecular interactions with what's called boiling point. Okay, so strictly speaking, boiling point is the temperature at which a substance would go from the liquid phase to the gas phase. But if we think about what's occurring when we boil a substance, is in the liquid phase, those molecules are right next to, butted up right against neighboring molecules, all right? And then we take them and we put a bunch of energy in there in the form of temperature, and we separate those molecules, right? When they're in the gas phase, they're floating around independently with a huge amount of distance between neighboring molecules. So in order to go from the liquid phase, where they're all touching each other, to the gas phase, where they're all separated out, you have to break these intermolecular interactions, right? So again, temperature is this stand-in for just how strong those interactions are. Do we have to put in a lot of thermal energy, or do we not have to put in a lot of thermal energy? Okay, so let's just take a look at a few compounds here. We're going to take a look at a very simple alkane, CH4. Let's actually do their Lewis structures here. And then we're going to start throwing some polar groups on there as well. We'll just keep one carbon. So now we'll add some polar groups, and we're going to compare melting points. And then lastly, we'll look at one with an OH group. Okay, so just for practice, everybody take a second, fill in any missing lone pairs that we see here. And then see if you can tell me what category, what functional group we see in each one of these molecules. Okay, our CH4, that's just carbons and hydrogens, all single bonds, so those are alkanes. We throw this carbonyl group in there, this would be an aldehyde. And then lastly, this OH group makes this molecule, what functional group for an OH group? Those are our alcohols. Okay? And these are three examples. They're not the exact same, but they're similar size. Each one just contains one carbon. All right, and again, we're going to compare their boiling points. The boiling point of CH4 is negative 162 degrees Celsius. Is that high or low?
Pretty high.
Negative, right?
Oh, negative.
Super low. So in this room right now, it's like 22, right? So we're talking about 200 degrees colder than this room right here. You have to get this molecule insanely cold. Even in the chemistry department, some of the best fridges that they have go to like minus 80 or something. Minus 150 is like a crazy low number, right? Which means that if we had this molecule in here, it wouldn't be in the liquid phase. We're already past its boiling point, so this would be present in the gas phase, right? You have to put almost no energy in to break those intermolecular interactions. If we take an aldehyde, now we have this polar functional group right here. This carbon double bonded to an oxygen, all right? Because of this polar functional group, these molecules can interact more strongly with neighboring molecules. So now our boiling point has increased to negative 19 degrees Celsius. Okay, and these aren't numbers you have to have memorized or anything like that, but we're just trying to spot trends here. And then if we take this molecule, now we have this OH group, which is not only a polar functional group, but it can also engage in what's called hydrogen bonding, which is even stronger than normal polar molecule interactions. And so now all of a sudden we have a boiling point up around 65 degrees Celsius. Okay, so on the one hand, we have our alkane, which is all the way down here at the non-polar end of our polarity spectrum. And we can see as we increase the polarity of these functional groups, getting to our very polar OH group, we increase the boiling point, right? Again, it just means that these alcohols are interacting more strongly with one another than our alkanes do. So for similar size, it depends on polarity. Okay. We will also see within just like talking about alkanes, if we're going to compare melting points, when we see an increase in the size of our alkane, we also increase its boiling point. Let's do this. So we had our example, our CH4, we said that that has a very, very low boiling point. Okay, let's start putting some more carbons on there. I'm going to use our bond line structures now. All right, so first of all, we want to be sure that we can convince ourselves that these are still all alkanes. Everybody take a second and just give me the chemical formula of each one of these here. Okay, so my first one was just CH4, kind of easy to see because all of our hydrogens are written. Can't really do a bond line structure of a molecule with just one carbon in there. How many carbons do I see in my next example though? 4. Remember, every endpoint and intersection, so that's a total of 4. And if we fill in with the correct number of hydrogens, how many do we get? 10. Okay, so now we're going to increase our number of carbons even more. Now we have a total of 6. And how many hydrogens on that one? 14. Okay, cool. So again, if we look at, we're comparing boiling points. All right, I'm just going to put down some numbers so we can prove to ourselves that they do indeed increase with the increasing size of our molecule. When we get to 4 carbons, this now has a boiling point of -1 degrees Celsius. And once we put 6 carbons on there, now we're at around 70 degrees Celsius. So the larger the molecule, the greater the boiling point. All right, so it's not the polarity, it's just the strength of those intermolecular interactions. These have what are called dispersion forces, which are, they're stronger the bigger the molecule, basically. So, strength of intermolecular interaction doesn't make it more polar, it just means that those weak interactions are stronger if you got more atoms. Okay, so 2 trends that we see. One, if we start sticking polar functional groups on there, we see an increase in our boiling point if we keep the molecules about the same size. All right, if we're talking about just alkanes, we'll also see an increase in boiling point depending on the size of that alkane. So the more carbons, the higher the boiling point is. Okay, so gasoline that you put in your car, is that going to have a few carbons or a lot of carbons? A lot, right? Why? How do we know that? Because it's a liquid, right? So it's got to have a few carbons on it. It can't be a butane. Well, you don't know the name of it. Can't be 4 carbons because that's a gas at room temperature. So it's a liquid. Yes, it's typically made of 6 to 10 carbon chains in your gasoline here. But yes, because it's that liquid phase, it's got to be on the longer end of your alkanes. Cool. All right, so alkanes, just about as non-polar as you can get, and then we discussed these intermolecular interactions here. We measure those through boiling point. We're going to transition to what's going to be a big part of this week, which is what's called nomenclature. Okay? Nomenclature, what we mean by that is the systematic, what's called IUPAC, naming of organic molecules. All right, this is one of these things that is going to seem super intimidating at first, but as long as you follow the steps that we're going to lay out here, it's not too bad. And the good thing about nomenclature is once you get the hang of it, every time we introduce a new functional group, we're basically just rinsing and repeating the same set of rules over and over again. What you don't want to do is try to sleep on it and think you're just going to guess these correctly throughout the rest of the semester. It doesn't work like that, right? You got to apply this set of rules that we're going to learn here. All right? So we're going to take a look at a few example molecules, and we're just going to kind of increase in complexity here as we go. So let's take a look at an example. We're going to start out with a simple 5-carbon alkane here, all on a straight line. All right, so step 1, we have to find and name what's called the parent chain. The parent chain in your molecule is the longest continuous set of carbons. All right, so for this particular molecule, it's a straight chain. There's not going to be any sort of branch points that we have to worry about. This would just be these 1, 2, 3, 4, 5 carbons. That's my parent chain for this molecule. We'll start sticking stuff off of this parent chain here in a bit, but for right now, we're just looking at these straight chains. Okay, so we got 2 things to worry about with our parent chain. The one first are these prefixes. Okay? The whole shtick in organic chemistry nomenclature is we need a name that will uniquely point to a molecule. So what we do is we build into that name the location of all of our carbons. All right? So we have a prefix that's going to tell us the number of carbons in our parent chain. Okay? I'm going to make a little cheat sheet down here, down at the bottom of my page here. Number of carbons versus the prefix. All right. I think the first 4 are kind of the toughest because they're very unique to chemistry. A 1 carbon has the prefix meth, such as methane or methanol, tells you that there's 1 carbon in there. 2 is eth. 3 is prop. And 4 is bute. All right. Those 4 are kind of the hardest to remember. The rest of them actually follow the same Greek prefixes that you would use in like a math class or a geometry class. So 5 is pent. 6 is hex. 7 is one that people aren't as familiar with. 7 is hept with a P and a T. H-E-P-T. What's the name of that 8-sided polygon, a stop sign? Octagon, so 8 is oct. 9 is non. 10 is dec. And truthfully, it goes on from there, but that's going to be enough for us. Okay, so here's our little cheat sheet of prefixes here. Again, one is, oh, sorry, not ET, ETH, F, my bad. Meth, eth, prop, bute, and then again it kind of goes to your geometry, pent, hex, hept, oct, non, and dec. So we need to build into our name how many carbons we have here. So what are we going to use prefix-wise for this example? Pent. Okay, and then the back half of the name, the suffix, is going to correspond to our functional group. All right, so for this one, we've just introduced this one type of functional group that we're going to talk about, alkanes. All alkanes have the same suffix, the same ending to the name of the parent chain, and that is just A-N-E. So this molecule is not just pent, but pentane. All right, I'm going to keep this page to do some notes. We're going to add some more rules here. So I'm going to jump to the next page and we're just going to practice what we just learned here. All right, put down some simple straight chain alkanes and y'all are going to name them for me. All right, so I got to count my carbons here. So this is that skill that we learned last week for our bond line structures, our endpoints and our intersections. So this would be 3 carbons. So what would be the name here? Propane. Everybody, I think, has heard of this molecule before. Most gas grills are run off of propane, right? So what's the thing running that grill? This molecule right here. That's what you're combusting to get that thermal energy. All right, this one here, how many carbons do we see? 7. 1, 2, 3, 4, 5, 6, 7. So we're going to use that prefix hept. So this is heptane. Cool? All right, so now we're going to make things a little bit more complicated. We're going to start sticking stuff off of our parent chain here. But that first step is going to remain the exact same. The first step in your nomenclature is to find that longest continuous set of carbons. That's what we deem the parent chain of a molecule. All right? So before we go on to naming things, let's make sure that we can find our parent chain in these more complicated molecules. So we're going to do one example together, and then I'm going to let you loose on a few others. right, so I'm going to find my longest continuous set of carbons here. And it's going to be kind of just a counting game. You're going to go through and count, see what the longest chain that you can make is. All right, so my parent chain here would be these 1, 2, 3, 4, 5, 6 carbons in my molecule. These are then sticking off of our parent chain. We'll learn how to deal with these here in a second, right? But for my parent chain, I need the longest continuous set of carbons. Okay? You could also have said 1, 2, 3, 4, 5, 6. That gets you the exact same number. That's perfectly fine. Okay? Either of those would give you the same name for your molecule. Generally speaking, we write our parent chain as a zigzaggy line that goes from left to right, but it's not always the case. So make sure that you're figuring out what your longest continuous set of carbons is. What I don't want to say is 1, 2, 3, 4. That's a continuous chain of carbons, but it is not the longest continuous chain of carbons in this molecule. All right, so that's the name of the game with nomenclature. Step 1 is to find your parent chain in a molecule. All right, so again, for this one, it'd be this here. This is what we would call our parent chain. These things sticking off of our parent chain is what we call substituents. And we'll worry about those here in a moment. All right, so find the longest continuous set of carbons in these examples. All right, how many carbons in our parent chain here? So we need the longest continuous. We can say 1, 2, 3, 4, but that is not the longest set of carbons in that chain. 1, 2, 3, 4, 5. Now I have a continuous chain that is the longest in that molecule. Okay, same thing over here. Don't be tempted to just always go with the left to right, 1, 2, 3, 4, 5, 6. We have a longer chain if we start up here. 1, 2, 3, 4, 5, 6, 7 is my parent chain. Okay, what about this one? How many carbons in my parent chain? 4. And now we have a different type of substituent, one of those halogens, but nonetheless, those are the number of carbons there. All right, we can even go a step further here. If I have a 6-carbon parent chain, what is the name of my parent chain?
Hexane.
Hexane. All right, and we wouldn't be done with naming this molecule. We haven't included the substituents, but that's the name of the parent chain in our molecule. What about 5 carbons? Pentane. Okay, 7 carbons, that was heptane. And 4 carbons, our parent chain would be butane. All right, but now we have all these carbons in this chloro group right here, unaccounted for. So how do we deal with things that are poking off of our parent chain, what we call our substituents? So that's step 2. Step 1 was the parent chain. Step 2 is to find and name your substituents. Okay. And again, we can just define substituents. This is anything that's off that parent chain, anything not included in the parent chain. All right. We're going to put down another example here. We're going to stick with our 5 carbon parent chain, but now we're going to stick a carbon off of that middle one. So step 1 is still the same, to find and name our parent chain. So this 1, 2, 3, 4, 5 carbons, that's our parent chain of pentane. But now we're going to stick something on the front here to account for all of those substituents on there. All right, we got to find and name our substituent. So my substituent, I found it. It's this carbon right here. Okay, how do we name our substituents? We're going to use the exact same prefixes that we did before, indicating the number of carbons. Okay. And I guess I should say that this is going to be specific to alkyl substituents, alkane substituents. Again, carbons and hydrogens, only single bonds. So we again got our prefix. If this is a 1 carbon substituent, what prefix am I going to use? Meth. And then for our alkyl substituents, our suffix is just YL. So the name of this substituent, it's got that 1 carbon, so it's a meth, but since it's an alkyl or an alkane substituent, it is a methyl group. I'm going to leave a little bit of room here to put some other substituents. We're going to go to step 3 here. Now we have to number the parent chain. I got to tell where that methyl group is in my molecule. All right. We do this by putting down what we call locants. We're going to number our parent chain. All right. So 1, 2, 3, 4, 5. So my methyl group is located on carbon 3. So this would be 3 methyl pentane. Okay, you run it all together, all one word. All right, so the 3 is the location of that methyl substituent attached to my pentane parent chain here. We can just sort of note, we use dashes between numbers and letters, and there is no space in our name. Run it all together, all one word. 3-methylpentane, rolls off the tongue. Okay? All right, so let's do another example here. All right, step one, you're going to find and name the parent chain, and then find and name our substituent. Okay, when it comes to the numbering, we're going to throw a little bit of a twist on here. All right, our parent chain, 1, 2, 3, 4, 5, 6 carbons. So what's our parent chain? Hexane. Okay, that's our parent. Our substituent is these 2 carbons right here. So what would the name of that substituent be? Ethyl. Okay. But now when we get to numbering our parent chain, we didn't have this problem in the previous example because this molecule was symmetric. But when we number our parent chain, we're going to number in both directions. All right? And then we're going to pick the numbering scheme that gives us the lowest number in our name. Okay, so we're going to number in both directions. We're going to look at it, and we're going to pick the numbering scheme that will give us the lowest number in our name. All right, so if we're going to go to our example here, I'm going to number from left to right, 1, 2, 3, 4, 5, 6, and then I'm going to number the other way as well, from right to left, 1, 2, 3, 4, 5, 6. And I'm going to look at which number would be in my name. So if I pick the blue numbering scheme, my substituent is at carbon 4. But if I pick the red numbering scheme, my substituent is at carbon 3. So which one do I want, blue or red? Red. We're going to pick the one that gives us the lowest possible number in our name. Okay. So this molecule here would be 3-ethyl hexane. Again, we'll run it all together, all one word. 3 is our locant, our location of that ethyl group attached to our hexane parent chain. All right, cool. So let's do a few more examples here. I'm going to put down some structures. You're going to name them for me. So let's start going through these. For my first one, I found my parent chain, those 4 carbons, so it's a butane. I have a 1 carbon substituent, a methyl group. I numbered my parent chain in both directions, and I picked the numbering scheme that was going to put that methyl group on the lowest possible number, which is how I got 2-methylbutane. Okay? We're going on to our next example here. How many carbons are in our parent chain? Cool. So, I'm really tempted to go left to right, 1, 2, 3, 4, 5, but there's an even longer chain. If we go 1, 2, 3, 4, 5, 6, which means that these 2 carbons are now my substituent, what we would call unethyl group. All right, I'm going to number my parent chain. 1, 2, 3, 4, 5, 6, and then I'm going to go the other way. 1, 2, 3, 4, 5, 6. So which one do I want, red or blue? Blue. I want that ethyl group on the lowest possible number. So that would be 3-ethylhexane. Okay. Again, my parent chain is the hexane. My ethyl group is off of the parent chain, and it is located on carbon 3. All right, my last example here, I got this 8-carbon parent chain, 1, 2, 3, 4, 5, 8, 6, 8. All right, this has a 3-carbon group off of it. We haven't seen one of these before. What would this be called? A propyl group. Okay, if I number my parent chain, 1, 2, 3, 4, 5, 6, 7, 8, or go the other way, 1, 2, 3, 4, 5, 6, 7, 8. Which one do I want? The red. I want my propyl group on carbon 4, not carbon 5. So this would be 4-propyl octane. Okay? And you can convince yourself that no matter which way you sort of numbered it for your parent chain, so for example, what I mean by that is, you could have also said that these 8 carbons were your parent chain, and this was your substituent, and you would get the exact same name. 1, 2, 3, 4, propyl octane. Okay? So, and then it doesn't matter as long as you find your continuous set, your longest continuous set of carbons. Okay. Cool. So then how do we deal with multiple substituents? All right, so first we're going to deal with multiple substituents that are identical. So for example, so we got these 2 examples here. And the first 3 steps are the exact same. Okay, so everybody take a second, find your parent chain, find and name all substituents, and then number your parent chain to give you the lowest possible number in the name. my first one, my parent chain is that pentane, those 5 carbons. But now I have not 1, but 2 methyl groups on there. So for identical substituents, we have to use our substituent prefixes. Got another table of prefixes that we're going to learn here. All right, so our number of substituents, and then our prefix. All right, I think these are Greek, but don't quote me on that. These are just like straight up kind of the normal ones that you would expect. If you have 2, it's di. 3 is tri. 4 is tetra. 5 is penta. 6 is hexa, and it keeps on going from there, but that's all we're going to need. Okay, so when I have these 2 methyl groups, I'm not just going to say like methyl in the name. I'm going to say dimethyl because there's 2 of them. All right, I did skip a step here. Our numbering 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Notice that in this case, it doesn't matter which one I pick. I have a methyl group on carbon 2 and a methyl group on carbon 4, no matter which one I pick here. Okay. Now, importantly, when we do our name, we do have to indicate the location of both of those methyl groups. All right. We have a methyl group on carbon 2 and carbon 4, so that's 2,4-dimethyl pentane. Okay, again, we're just going to make a note. We have to include the locant of both methyl groups. Okay, and that is the same regardless of whether they're on the same carbon or different carbons. There needs to be 2 locants in there, 1 for each methyl group. So given that, see if you can't name our other example here. All right, and again, you should have 2 locants in your name when you're done. All right, my parent chain, 1, 2, 3, 4, 5, 6. This is a methyl group. This is a methyl group. Oops. Okay, I'm going to put in my numbering. 1, 2, 3, 4, 5, 6. If I went the other way, those methyl groups are on carbon 4, so this is my numbering scheme I want here, okay? And when I put together my name, I have to put the location of both of those methyl groups. So 3,3-dimethyl hexane. Everybody remembers to put them both when they're on different carbons. And everybody forgets you got to put them both even when they're on the same carbon. All right, so we're going to do this example specifically to make a note. Include the location of both methyl groups even when they're on the same carbon. because 3,3-dimethylhexane is a different molecule than 3,4-dimethylhexane, et cetera, right? We got to uniquely point to one structure with our name. Okay, so our last step, and we've been doing it all along here, but let's just say, because we're going to add a new rule, last step in numbering is just to assemble the name. And what we've seen thus far is it always goes locant dash substituent and then your parent. Right, all run together as one. All right, and so we dealt with if we have multiple substituents that are identical. All right, what if they're different? We don't really do much different until we get to that step when we're assembling our name, and then we just assemble in alphabetical order. So let's take a look at some examples here.
So the locants, do those follow the numerical order, or do they follow the order of where?
So you put both in, and you want to pick the one that will give you the lowest number in your name.
Totally. I just meant like, so when we're doing the two different substituents, does it follow that order?
This would be like you put them in alphabetical order. So let's just do this first one together real quick. All right, so I'm going to find my parent chain. 1, 2, 3, 4, 5 carbons. I have two substituents. This one carbon substituent up here would be a methyl group. And this 2 carbon substituent down here would be an ethyl group. I'm going to put in my numbering scheme. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right. I'm going to compare these two numbering schemes by looking at what numbers would end up in my name. If I pick the blue numbering scheme, it would be a 2 and a 3. And if I pick the red numbering scheme, it would be a 3 and a 4. So which one am I going to go with? The blue numbering scheme. I want the lowest possible number in my name. Okay? So now when I assemble my name together, I got to put my substituents out front, but I'm going to assemble them in alphabetical order, which means which comes first, the ethyl or the methyl in my name?
Ethyl.
The ethyl. And that ethyl group is located on carbon 3, so 3-ethyl, followed by my next substituent, 2-methyl, and then my parent chain, pentane. So 3-ethyl, 2-methyl, pentane. Each substituent and its locant, but they're assembled in alphabetical order. Cool. All right, I'll give you a few more minutes to do this last one here. Okay, how many carbons were in our parent chain? 1, 2, 3, 4, 5, 6, 7, 8. All right, we got two substituents. One of them is 3 carbons. That would be a propyl group. The other one is 2 carbons, so that would be an ethyl group. I'm going to number 1, 2, 3, 4, 5, 6, 7, 8. So my blue numbering scheme would put a 4 and a 6 in my name. If I go the other way, 1, 2, 3, 4, 5, 6, 7, 8. That would put a 3 and a 5. So which one am I going to go with? Red. I want the lowest number in my name. And I'm going to put together, I'm going to assemble now which one of my substituents is going to go first in the name. Ethyl, right? The ethyl comes before propyl. E comes before P. So this would be 3-ethyl, 5-propyl octane. Okay? So, as we said, assemble our name. Okay, and we can say if we have multiple, we need to assemble in alpha order. So again, this naming scheme is what's called the IUPAC naming scheme, the International Union of Applied and Pure Chemistry, something like that. Anyways, back in the day, if you think about like science just sort of starting up, you had everybody doing things differently. This organization came in and said, whoa, we got to call our molecules the same thing as you're calling your molecules, right? So they laid out this set of rules. They have rules for literally everything, all right? There's one more pain in the butt situation that is pretty rare, but it can occur, and they have a way around it here. So we're going to take a similar molecule to what we did before. I'm going to put an methyl group over here and an ethyl group over here. Okay? This has our same 1, 2, 3, 4, 5, 6, 7, 8 carbon parent chain. On the one half, we have an ethyl group, and on the other half, we have a methyl group. And now we're going to number our parent chain. 1, 2, 3, 4, 5, 6, 7, 8. Or we can go the other direction. All right, and remember, what is our rule for picking our numbering scheme? We want the lowest possible number in our name. But if we look at our blue numbering scheme, we have a 3 and a 6. And if we look at our red numbering scheme, we have a 3 and a 6. Okay, so we got a problem here. It's a tie. And you can't just pick whichever one you want because we need to uniquely point to one molecule. So they have a tiebreaker rule in place here. Okay, so if, and let's actually put this under our numbering rules here. Okay, we're going to say if and only if there's a tie, we break that tie with alpha order. Whichever substituent comes first in the alphabet will be the one that gets the lower of the numbers. All right, now, this is rare. This only happens if there's a tie in your numbering scheme. A lot of people like to just default to alpha order all the time. It doesn't work like that. If you can, you need to build the lowest number into your name. But if you look, and both numbering schemes give you the same numbers, there's a tie in your numbering scheme, then and only then do you break that tie with alpha order. Okay? So that's why we name our substituents when we put them in there. So we can see that in this case, ethyl comes before methyl. So which numbering scheme would I pick, red or blue? Red. I'm going to pick the numbering scheme, since there's a tie, that gives the first in alpha order the lower number. So 3 ethyl, 6 methyl octane. Okay? So, don't get me wrong, this sounds like a beast of a set of rules to being applying at first, right? Whereas start you off fairly simple in terms of your assignments, you know, name the easier ones, things with just one substituent on there, and then there's another assignment that has throwing these sort of more difficult rules in there, okay? The good news is that once you get this down, we're literally just going to do the exact same thing for every functional group. We talked about how alkanes have this A and E ending. All we're going to do is swap around what that ending is when we get to alcohols. Alcohols have an OL ending, but we're going to follow the exact same set of rules every time. So, pain in the butt. This is really what this alkane chapter is kind of about, is introducing you to these nomenclature rules, because alkanes don't have really very many interesting reactions, so that part's kind of small, okay? But once we get this nomenclature scheme down, we're just going to kind of rinse and repeat. This tends to be where people clean up in the course, because again, once you get the rules down, you can get all those points pretty easily on an exam, okay? So bottom line is, put in the practice now to make sure you got your footing right, and then when we build on it, you'll be fine, okay? Cool. All right.